So welcome to lecture number 20 of the Statistical Thermodynamics course. We laid the foundation that for a two-particle system, what will be the steady-state version of the Schrodinger's wave equation. And we also said now we need to separate the internal and the external energy modes. So for that, if you recall, we wrote that V12 is a function of R only. And for a two-particle system, two-particle system, okay, which experiences only the central Coulombic field. Okay, so V12, as we said, can be written as VR. R is basically R2 minus 1. Okay. And the wave function can be written as 2. This is the total mass, if you recall. This is the Laplace operator. Is 2 mu psi into psi epsilon into psi. So this is called this is a steady-state version of the Schrodinger's wave equation. And the Hamiltonian operator we already know. Okay. So H external into psi external. This is the wave function due to the external energy mode. By 2 mt into r square psi external, which is equal to energy external to psi external. Because as we know that these two are due to the relative motion. It's excluded. Internal, H internal to psi internal will be equal to the reduced mass mu. This time it will be the R, that is a separation. Psi internal, okay, is equal to plus, now you have the VR, which is the internal potential. Internal energy internal to psi internal. Okay, so the total psi, the total wave function, written as the psi internal into psi external, energy is equal to E external E internal. Okay. So what we did was that this is the Hamiltonian for the external wave function, which is given by, remember your R. R is basically the, go back, slides. R was this, is the center of mass. Okay. So it is like the movement of the center of mass, so to say. So that takes care of the external, and the total energy is like this. Whereas when we go to the internal Hamiltonian, the internal energy modes, it is basically dependent on small r, which is the separation distance between the two masses. And that is given by this. This is the reduced mass, if you recall. VR, we said, is always dependent on the relative distance between the two particles. And it is given, therefore, by this. So these are the two separated forms. And the total wave function is actually multiplicative. The total energy is additive to begin with. Okay? So in spherical coordinate system, and we will have a separate lecture or a tutorial on spherical coordinate system, so that there you can be more conversant of what it is. So this is for the internal energy mode. Okay. So is the internal wave function. psi. So now if you spread out and write the total thing in a spherical coordinate system, basically the Laplace operator, okay, you will find it. So this is basically the Laplace operator. So if you try to do that, you will find square. This is a long equation, so bear with me. Yeah. Plus 1 over r square sine theta d by d theta sine theta d by d theta, and plus 1 over square sine square theta d square phi by d square phi internal. Okay, so as you can see that this is how you write the Laplace operator in the spherical coordinate system. So this requires a little bit of brushing up on your part. This Laplace operator is very common. Okay, so this is basically now minus the dr phi internal is equal to 0. All right. So this is how it is written in the spherical coordinate system, the internal energy part of the wave function. And internal and external are independent, as you saw earlier. So psi, therefore, is r theta phi. These are the three coordinates, r theta phi, for a spherical coordinate system. That is given as r into y theta comma phi, first level of separation. So now, when you back substitute this separation into this equation now, substitute it here, okay, given as y theta comma phi r square d by dr square, yeah, first term, okay, plus this is again a long equation, so bear with me. Small r square sine theta, okay, by d theta, theta, d theta, okay, plus r over small r square theta square y square plus 2 mu h r square internal r r by y is equal to 0. Okay, we do now a little, so you can see this is a very complicated equation. We have separated it out a little bit. So arranging, I think what you do is you're arranging. Okay, this is y theta comma phi divided by r square d by dr square dr by dr plus r comma r divided by r square. Sorry, just need a little bit here. So plus 1 over y sine theta by d theta theta dy by theta plus r over r square sine square theta y square plus 2 mu by h bar square r y theta comma phi is equal to 0. Okay. Okay. Okay, it's a small mistake on my part. This expression I wrote it down. Just a second. So this becomes, sorry, 2 mu r square divided by h square r is equal to 0. Okay, so that's the total expression. So, right now, what we do now is basically you separate the two things to the two sides, like you do in a typical separation of variable. So it will be or 1 over r d by dr square plus 2 mu squared by h bar square e internal minus vr, which is equal to, so the right hand side is all r minus 1 over y sine theta d by d theta theta dy by d theta. Okay, minus 1 over y sine squared theta d square y I square, okay, is equal to, say it is equal to minus alpha. Right? Okay. Okay, so that is the expression that you get by separating out. So this part is a function of r, this part is a function of theta and phi, and this is basically the constant that you are dealing with. Okay. So if you now separate the two things out, or it will be 1 over r d by dr squared d capital R by dr, okay, plus 2 mu squared by h bar square to the internal energy minus Vr minus alpha into capital R is equal to 0. So that's the first expression. Okay, and the other one, so this is one. Second one. Okay, so let's write it as plus R. Come to that why it is. Second one is 1 over sine theta d by d theta sine theta into y by d theta plus 1 over sine squared theta square y over d phi square plus alpha y is equal to 0. Second one. Okay. Now, similarly, y, as you know, is a function of theta comma phi. So this can be written as a t theta e phi. Okay, all right. So this can be further then broken up to p sine theta d by d theta theta dt by d theta plus t by sine squared theta d squared p by d squared plus equal to 0. Okay, now 1 over sine theta d by d theta sine theta dt by dt plus alpha minus beta sine squared theta equal to 0. All right, equal to 0. And the other expression is d squared b by d phi squared plus beta b equal to 0. So as you can see, this is the third one. So as you can see, alpha and beta are constants. So how many equations did we get? We got this expression, which was with the function of r. Then we got this expression, which was a function of theta, and this expression, which was a function of phi, because of r, theta, phi. Okay, three expressions, and out pops two constants, alpha and beta. Alpha was to separate r from theta comma phi. Beta was to separate between theta and phi, right? So the limits are r varies from 0 to infinity. Theta, of course, varies from 0 to pi, and phi is from 0 to 2 pi. So this is a spherical coordinate system. The limits. Okay, so we have basically what, three ODEs. Okay, with alpha, beta, and E internal unknown constants. Correct? Alpha, beta, and E internal as unknown constants. Correct. So now let us focus on one by one what we can do with this. So first, let us take a look at the rotational mode. The rotational mode, call that phi. Okay. So the solution to this actually lies dE by square plus beta p is equal to 0. Okay. So solution to this, and E phi is equal to exponential I m phi divided by, okay, where m is equal to root over beta is equal to 0 plus minus 1 plus minus 2 da, da, da. Okay. And this also obeys pi plus 2 pi equal to, right? So let's take a second pause and let's look at it. So this is the rotational mode, which is given by p pi. Okay, and this is the expression. Okay, and then if we solve this p phi, it is given in this particular form, where this is m is nothing but root over beta, and is given by 0 plus minus 1 plus minus 2, and with the argument that p is a periodic function, so phi plus 2 pi is equal to the p phi once again, right? Okay. So this gives you the first expression. Okay, so now define transformation. Define a transformation. Okay, what is the transformation? Say define omega equal to cos theta. So therefore, 1 over sine theta d by d theta sine theta dt by d theta plus alpha minus beta sine squared theta t was equal to 0. This we remember, this is for the theta. Now if we replace omega equal to cos theta in this particular expression, so what do you get? D by d omega 1 minus omega square dt by d omega plus alpha minus m squared minus omega squared t is equal to 0. Okay, so sine theta is 1 minus, so sine square theta is 1 minus cos square theta. So this expression, if you look at it closely, okay, this particular expression over here, if you look at it closely, this is called the Legendre's equation. It comes from spherical harmonics, actually. Spherical symmetry, anything that shows spherical symmetry, the Legendre's equation. So this obviously usually has a power series solution. And the series is truncated to ensure finite solutions at omega equal to plus minus 1. Okay, all right. So this is Legendre's equation, and this has got a power series solution, and the series is truncated to ensure finite solutions at omega equal to plus minus 1. So truncation leads to well-defined solution. Remember that the wave function has to be well-defined and all those things. Well-defined solution if and only if, that is if alpha is equal to j into j plus 1, where j must be greater than equal to delta n, or modulus of n, and the solution t omega, okay, now because we have substituted theta with omega, is given as 2j plus 1 into j minus mod m factorial divided by 2 j plus m again factorial. Okay. And this entire thing is raised to the power of half multiplied by pj omega. So out of that, this pj modulus of this m is basically called the Legendre's polynomial. Legendre's polynomial of order m and degree j. See if you have, so this is a mathematical manipulation right now. So truncation leads to well-defined solution if and only if alpha is j to j plus 1, and j must be greater than equal to m, where m we know is root over of beta, okay, and it has got that 0 plus minus 1 etc. Okay, and the total solution then becomes t, which is the theta part of the solution, is given by this multiplied by this polynomial, which is pj. This is called the Legendre's polynomial of order m and degree j. So this is the total solution. Okay, so the total solution. So what if I open up the Legendre's polynomial? Let's write that also. J over n omega is given as, again complicated, j factorial 1 minus omega square w, whatever you call it, 2. Then we write it like this: is the differential plus j divided by d, but this is the lower part of the differential. Okay, omega square minus 1 j. So this is the order of the differentiation. So this is the order differentiation with respect to omega, and this is done on omega square minus 1 raised to the power of j. So this is the Legendre's polynomial. So the total solution becomes total solution. Now we're in a position to write it. Is given as y j m theta comma phi It's given as 2j plus 1 into j minus whatever the modulus of m factorial divided by 4 pi j plus modulus of m factorial. Entire thing is raised to the power of j modulus of m cos theta e I m. Okay, so various solutions for different values of j and m. J and m are called spherical harmonics. So j is therefore the rotational quantum number, and m is called the magnetic quantum number. Okay. So various solutions for different values of j and m are possible. These are basically called the spherical harmonics, and j has got the official name of this called the rotational quantum number, and m is called the magnetic quantum number. Okay, so from this total solution y, which concerns with theta and phi, this is the solution that we get. So quick recap, what did we do? We found out the rotational mode. For the rotational mode, we first did phi, then we defined the transformation. We then cast it in this particular form, which is basically nothing but the Legendre's equation, well known. It's a power series solution. The series is truncated to ensure finite solutions, and truncation leads to well-defined solution if and only if alpha is like that. And then we wrote that this is cast in terms of the Legendre's polynomial, and Legendre's polynomial is of the order n and degree j to the modulus of m, because m can be plus minus. And then, of course, the Legendre's polynomial is written in this particular fashion. Then the total solution becomes this. Okay, and this has got various solutions for different values of j and m, and these are called spherical harmonics. And j is therefore called the rotational quantum number, and m is called the magnetic quantum number. So rotational and the magnetic quantum number. Okay, and therefore this marks the end of the theta and phi solutions. In the next class, we will see what happens to r, the r part of the solution. That we are going to cover in the next class. Thank you.